Hi everybody, thank you very much. I'm really excited to be here. Thank you all for coming. And I'm really excited to share with you some results of a new research I've conducted, which allows to automatically detect vulnerabilities in black box routers. Now, by black box, I mean routers which we do not have access to their binary code or source code. Thereby, we cannot actually reverse engineer them. And by automatically, I mean that once an initial setup phase is complete, the vulnerabilities are detected with no further manual assistance. Now, I lie a little here in this title. The method I'm going to present does not really directly find vulnerabilities. It finds deviations. I will shortly describe what they are. But it turns out that many such deviations turns out to be vulnerabilities. This research was done in collaboration with Adi Sosnovich and Orna Greenberg. Before we begin, just a quick introduction, a few words about myself. I'm the chief research scientist of a national lab in Israel, which is operated by an aerospace and defense company called Rafael. I'm a former visiting scholar at Stanford University. I also serve as a senior adjunct lecturer and research associate at the Technion in Israel. And I mostly spend my days doing network security stuff, which is a lot of fun. I recommend to all of you to try it. Okay. So here's the outline of my presentation. First, I will discuss the whole motivation for this research. I will then, of course, describe the method that we propose. And then I will touch on a major building block of this method, which is symbolic execution. Afterwards, I will talk about the unique optimizations that we devised in order to make our method actually practical, scalable, and efficient. And afterwards, I will discuss the application of our method to a Cisco router, or specifically the OSPF routing protocol implementation of a Cisco router, and then the vulnerabilities we have found. Okay, so let's talk about motivation. As we all know, network protocols are based on open standards. There is an organization called the IETF, Internet Engineering Task Force, that creates those standards in an open process, and everybody can contribute to this creation of standards. You just have to register to the appropriate mailing list, and you are good to go. Just fire away with your emails. And of course, those standards are actually freely available as RFC documents, like the one you see over here. And anybody can read it, review it, and find security bugs and other deficiencies in the protocol, which is great. However, the internet mostly runs on these babies, closed source proprietary routers made by big name vendors like Cisco. Now, in theory, these routers should implement to the letter the standard protocol. However, we are not guaranteed that they are exactly implementing the protocol. So we would like to find those hidden deviations of the implementation of the protocol in those routers as compared to the standard protocol. Now, these hidden deviations can be either deliberate or inadvertent, for example, due to bugging codes or, I don't know, misunderstanding of the standard. And so these hidden deviations might be the cause of logical vulnerabilities in the router. By logical vulnerability, I mean that the router makes incorrect decisions with regard to the functionality of the protocol, and thereby compromising the security of the network. Now, it doesn't have to be that a deviation will necessarily lead to logical vulnerability, but this is often the case, and you will later on see in the Cisco case, especially if those deviations are inadvertent. So we would like to find those hidden deviations, but doing so demands a lot of efforts. We need to get the binary code of the router. We need next to reverse engineer the code, and then compare the functionality with that of the standard protocol, and it's a lot of hassle. Instead, so what we propose is actually the goal of our research is an automated formal black box method that should unearth those deviations. Again, the deviations of the protocol implementation in the router as compared to the standard protocol. And by black box, I mean that the method does not require an access to the binary code or source code of the router. We only observe its external behavior, like the route or external state, like the routing state of the protocol of the router, routing tables, or all the packets the router sends. Only the external behavior, which we can observe. By formal, I mean that the method is systematic and relies on rigorous foundations. Now, it doesn't mean that we actually will discover all deviations. We don't claim that. But we will likely find more deviations, deviations that may have gone unnoticed until now. And by automated, I mean that once an initial setup phase is complete, we can find deviations with no further manual assistance for various models and various routers and protocol implementations. Okay, so here's the basic idea of our method in a nutshell, which is absolutely completely simple and very straightforward. We would like to compare the behavior of the router, which we call SUT, system under test, to a model router that captures the standard functionality of the network protocol, okay, or part of it. For example, if you want to analyze just a specific part of a protocol, then the standard router will only capture this part of the protocol. So we would like to actually compare the behavior of the real router to a standard router which captures the standard functionality of the protocol. Actually, what we really want to do is actually compare the behavior of a network model which captures the standard functionality of the protocol to a real network with real routers and actually compare their behavior. If the behaviors of the two networks somehow mismatch for some reason, then we find a deviation. Okay, now notice that in both networks we have here an entity called an attacker. This attacker, the job of this attacker is actually to send a sequence of protocol messages to the rest of the network. This attacker actually drives different behaviors of the network. Different sequence of packets that sent by the attacker will exhibit different behavior of the network. So we would like to actually, for a given sequence of packets sent by the attacker, we want to examine the behavior of the network model that captures the standard functionality of the protocol against the real network. Each such scenario we call a test case. Okay, so what we need now to do is actually find a way to generate those test cases. And a naive approach might be to just manually generate those test cases based on our understanding of the protocol, based on some predefined heuristics, based on fuzzing, and so on and so forth. But this may cause us to not cover the entire functionality of the protocol and may cause us to miss deviations. So our approach here is to automatically generate tests based on a well-known procedure called symbolic execution. For those of you who are not familiar with symbolic execution, I will explain what it is in a minute. So we use this procedure, this symbolic execution, to produce tests that will cover the entire functionality of the network model. This will allow us to actually test the behavior of the routers in each and every corner case of the protocol functionality. So here's our method in a glance. Afterwards, I will dig into each of these steps. First, we need to construct a network model, again, that captures the standard functionality of the protocol, of the network protocol. Then we apply this, the symbolic execution on this model. The symbolic execution will produce a set of tests that cover the entire functionality of the model. These tests are then executed on the real routers, on the actual network, and it will actually produce an outcome for each test, and this outcome will then be compared to the expected outcome as predicted by the network model. If there is a mismatch between the network model again and the real network, then we have a deviation. Okay, so let's now talk about the first phase of our method, creating the model for the protocol. Okay, so a network model is a fancy word just to describe a program that captures the standard functionality of the network protocol in a given network topology. Now you can write your own network model from scratch. This is what we actually have done for the OSPF case. But you can also take another open source implementation of the protocol. This is what we have done in other cases for the research, which I will not detail. And we can call this open source implementation our model. And actually, if the open source implementation was developed independently of the black box router, then we are okay. It just means that the deviations we will find are deviations of the black box router as compared to the open source implementation we are finding, which is the network model. Okay, so the aim here is again to create this network model, which can implement the standard functionality, the entire standard functionality of the network protocol or part of it. And of course, the input of this program, this network model, is actually just the sequence of packets sent by the attacker. Okay? This is, again, I remind you that there is an attacker entity here that sends sequence of packets that drives different behaviors from the network. So the network model accepts inputs from the sequence of packets sent by the attacker. Okay, and then we apply this procedure which is called symbolic execution. And symbolic execution is the procedure that allows to trace all execution path of a given product, of a given program, and generate the input that will trigger each and every execution path for that program. And it does that by simply denoting each input in the program as a symbol. For example, here in this example on the slide, you see here a program with two inputs. And they are denoted by A, the first input, and by B, the second input. And this means that each program variable is now an expression of those symbols. And each branch or each conditional branch here in the program actually set constraints on those symbols. For example, if you want to trace this execution path passes through three conditions, which means that we have three constraints on the symbols, which are here, which are circled here. Which means that if we want to trigger this execution path, we need to meet all those constraints. In this example, we must have that A plus 5 must be greater than 0, A plus 5 must be greater than 2, and B must be equal to 2,789. If all those conditions are met, then we have this execution path. For example, if A equals 0 and B equals 2,789, then we have this execution path. And we can do this for each and every execution path in the program. For example, here is another execution path. It also passes through three conditions, so we have also three constraints on the symbols. And here you can see that if you put all the constraints together, they are unsatisfiable, which means that there is no value for those symbols for A and B that satisfy those conditions, and which means that this path is infeasible. Okay, So we apply this symbolic execution procedure on the network model, okay? And this means that we actually trace all the execution path of our network model. We actually trace all the different behaviors of the network model, and we find out which input of which packets the attacker should send to the different routers in the network in order to trigger all the execution paths of our network model. For example, here you can see an example of a test case in which the attacker sends a routing message M1 to router 1, and then message 2 to router 2, and then message 3 back again to router 1. And this is the sequence that the attacker sends, and it triggers a certain behavior of the network model, and the expected outcome is the routing states of all the routers in the network model. And this again allows us to generate all the necessary test cases to cover the entire functionality of the network model. Now, at the third step, we execute those test cases on the real network. We take, again, the example test case I showed earlier and send the necessary messages to each and every router in the real network this time. And after I send all these messages in the real network, I get the actual outcome in the real network, which is all the routing states for all the routers in the real network, in the real actual routers. And then, of course, I can compare the actual outcome to the expected outcome from the network model. I actually compare the routing states of the routers in the real network to the routing states of the routers in the network model. And if there is a mismatch, then I found a deviation. And once I find those deviations, I can now try to analyze if they indeed poses a security threat to the network or not. This can be done very easily because I can really trace all the packets sent throughout the test, both in the network model and the real network, and see the core or the root cause of this deviation. Now, this is all well and good in theory. However, if we wanted to test or analyze a complex real-world protocol, like, for example, the OSPF, which I will mention later on, then probably we will need a lot of test cases in order to cover its entire functionality. This is because we have a lot of execution path throughout the network model. This means that actually, if we have too many test cases, then our method is simply inefficient or possibly impractical. So in order to overcome this difficulty, we created or devised unique optimizations that allows us to deal with these scalability issues. And these optimizations actually allowed us to dramatically reduce the number of tests we need, but still maintaining full coverage of the network model. This is very important to us. So we want to still maintain full coverage of the network model, but we just reduce the number of tests. Now, I will not go into the details of this optimization. I will just describe our main optimization with general intuition. So, for example, here you can see we have here 100 test cases of length of one message, which means that in each test case, the attacker sent just a single message. And now we have a single message. Actually, all the 100 test cases represent a different message sent by the attacker. But in all those test cases, the final state of the network model was the same state. Here it is denoted as state X. Now, if we have these 100 test cases, then we must have an additional, on top of those 100 cases, another set of 100 test cases, this time with that has two messages in each test. The first message is one of the 100 messages in the original test cases, and the second message is another message. We call it message M, which is common to all the 100 test cases. Now, as you can see here, the difference between the upper 100 test cases and the lower 100 test cases are not that great. We do not cover a lot of ground here due to the lower 100 test cases. What's missing is only the passage between state X and state Y using message M. So we can actually replace those additional 100 test cases with just a single test, having a single message, message M, while the initial state of the test should be state X. So here you can see very easily that if we take the lower test here and combine it with the tests, with the original 100 tests up in the slide, then we do not lose coverage of the network model functionality. But still we manage to reduce dramatically the number of tests. Now all the 100 test cases having 2 messages long are not needed anymore. So this is a rough intuition of how we can reduce the number of tests without compromising the full coverage of the network model. Okay, now let's talk about the application of this analysis of this model or this method to the OSPF routing protocol. The OSPF is the most widely used and most complex routing protocol on the internet. This is why it's very interesting to analyze. Now, for those of you who are unfamiliar with the protocol, let me recap or just say a few words about it. So OSPF works by having each router send out a routing advertisement called a link state advertisement, or for short LSA. LSA is just an advertisement that says what are the links of the router, or in other words, who are the neighbors of a given router. And this LSA, each LSA of a router is flooded throughout the network. So every other router receives all the LSAs of all the other routers in the network. Here's an example, illustration of this. Here you can see the network with a few routers. Now R1 will send its LSA, which will be flooded throughout the network. And now everybody knows that R1 is connected on one interface to the stub network and on the other interface to R2. When R2 sends its LSA, it is flooded again, of course, throughout the network. And now everybody knows that R2 is connected on one interface to R1 and on the other 2 interfaces to these 2 other routers. And so on and so forth. Each router builds its own view of the network topology. Based on this view, routing tables are constructed. Now, let's say, now I will now touch about a very important security mechanism in OSPF, which is called the fightback mechanism. Let's say we have here now an attacker which resides within the network. Now, this attacker can simply send out false LSAs on behalf of other routers in the network. For example, it can send out a false LSA on behalf of the victim router in the bottom of the slide. So let's say it does that. And it sends out the false LSA, which means that now everybody receives this false LSA with the false link. And now, for example, everybody thinks that this router, the victim router, is disconnected from the network, in this example. So every router receives this false LSA, including the victim LSA. Okay, so once the victim LSA receives this false LSA, which was advertised on its behalf, it immediately notices that something wrong, and it will immediately send out a correcting LSA, which we call it the fightback LSA, with the correct information. Now, since the false LSA was advertised with a sequence number that equals X, every LSA has a sequence number, so the fightback LSA will be simply sent out with a sequence number X plus 1. So everybody will know that the fightback LSA is newer and it will run over the false LSA. So this is a fightback mechanism. Now an attacker aims is to actually find a way for its false LSA to somehow be persistent in the network. He wants to find a way to evade this fightback mechanism and actually make the false LSA, it advertised to all the routers in the network, stay in the network and be persistent and will not be reverted quickly by the fightback. Okay, so a few words about our OSPF model. Here you can see a snippet of it. So as I said, we modeled the OSPF, actually the core parts of the OSPL standard using just a simple program of Python. It took us roughly 1,000 lines of code. We could have just taken another open source implementation of OSPF, but we chose to do it ourselves because we wanted to implement just the parts which are important for the fightback mechanism, because we wanted to make sure that the fightback mechanism is implemented correctly. So we implemented the flooding procedure and the fightback mechanism, and for this network model, all the other parts of the OSPF we didn't actually implement it. So this is a snippet again of our code. And okay, so just a minute, I will back up here. So actually what we have done is to run symbolic execution on this Python program. This symbolic execution gave us a set of tests that cover the entire functionality of this Python program. And then we executed those tests on a real Cisco routers, on a network of real Cisco routers. Here we leveraged network emulation softwares suites that are called GNS3 and Viral. They are both network emulations software that allows to run real software images of Cisco on a PC. That was really handy because it allowed us not to actually build a complete setup of hardware routers in our office. So it was very easy, but it was absolutely equivalent to hardware routers. This is the actual software run on those routers. We used 3 different images of Cisco. The bottom one is the most recent, most up-to-date image we had at the time of our research a few months ago. And the bottom line is that we found in those test cases 7 deviations of Cisco as compared to the standard functionality. 6 of them turned out to be indeed logical vulnerabilities. 1 of them was a non-vulnerability. Actually, all the 6 that were turned out to be vulnerabilities were inadvertent deviations. The one that was a non-vulnerability was actually deliberate deviations from the standard made by Cisco. 2 of the 6 vulnerabilities were absolutely new vulnerabilities we have found in the most up-to-date Cisco image. This is the CVE you see on the slide. And actually those new vulnerabilities allows the attacker to evade the fightback mechanism and allow the attacker actually to send false LSA and make them persistent in the network, and actually allows them to persistently poison routing tables of other routers. The vulnerabilities we have found affect all iOS, XE, and ASA products of Cisco, and also some Nexus products. So you can see this covers dozens or maybe hundreds of products of Cisco. Before I describe the vulnerability, let me just give you one more piece of information about OSPF. We said that every LSA has a sequence number, and if an LSA has a higher sequence number than another LSA, then it's considered newer and it will run over the older LSA. Now, what if 2 LSAs have the same sequence number? So the OSPF standard states that there is a tiebreaker. We use the tiebreaker as a checksum value. If the checksum value of one LSA is higher than the checksum value of the other LSA, then the one with the higher LSA will be considered newer. This is just an arbitrary tiebreaker. Okay, so here is the general outline of the attack, of the new attack we found. So let's say we have here the network with the attacker. Now in this attack, the attacker sends out false LSA with invalid link, while the false LSA has a sequence number that has the maximum value, okay? Now, in this case, when the victim receives this false LSA, it should react with a fightback LSA, as we saw earlier. But now, because the false LSA has a maximum sequence number, it cannot simply send a regular fightback message with a higher sequence number, because the false LSA has the maximum sequence number. So what the OSPF standard says is that the router should now send a fightback LSA, a special fightback, with the maximum sequence number, the same sequence number as the false LSA, and with an age, with the maximum age. The age, every LSA has an age field, which simply states how many seconds the LSA has been around in the network. So this fightback will have a maximum age, and this will have the effect of simply flashing out or deleting entirely the LSA in the network. So nobody will have any LSA after this fightback. And then in the second stage, the victim router will be able to send another fightback LSA with the correct information, with, for example, a sequence that equals to 1, back to the minimum sequence. So now in this particular case, in this special fightback, the standard says that this special fightback has to include the invalid links as advertised by the false LSA, as advertised by the attacker. Okay, the invalid links should be in this unique fightback message. This is in order to make sure that the checksum value in the fightback, in this unique fightback message, will be the same as the checksum value in the false LSA message sent by the attacker. Unfortunately, Cisco did not implement this correctly. And it actually sent out, as usual, the valid link in this special fightback message, which meant that actually the checksum value of the fightback message was different than the checksum value of the false LSA message. And now it depends on the actual values of the links sent by the false LSA and the fightback LSA, but it meant that there is a chance that now that the checksum value of this unique fightback message will have a lower value as compared to the checksum value of the false LSA. Now in that case, this means that all the other routers in the network will consider the fightback message sent by the victim router as older than the false LSA, and they will all ignore this fightback message, and they will simply keep they will keep the false LSA sent by the attacker, and in this way the attacker will be able to persistently poison the routing tables of all the routers in the network. All the routers will simply hang on to the false LSA. And this is actually the main motivation, the main vulnerability we find in Cisco, and oddly enough, we ran the same tests on Quagga. Quagga is an open source, a very popular open source routing suite for Linux machines, but we treated it as a black box, and we actually tried to find deviations also for Quagga in our method, black box method. And we also find the exact same vulnerability in Quagga. This is the CV for Quagga. So it was interesting enough that we have seen the exact same deviations. Actually, for Quagga, we only found these deviations as compared to the Cisco case. Okay, so to wrap up the presentation here, in summary, what we've found here in this research is a method that allows to automatically find deviation in black box routers As you noticed here, all the procedures we used here are actually standard procedures, like symbolic execution is a well-known procedure. But the crux of the method here is actually to use the appropriate optimizations that allows this symbolic execution to scale and to be practical. And I think the main takeaway here from all this research is that we should, as a security community, try to, instead of using some ad hoc methods, try to use as much as possible systematic procedures, such as the symbolic execution, that will allow us to find new vulnerabilities. If we are using them correctly and in an optimized way, they will be practical and will allow us to find new security vulnerabilities in many products. So with that, I will be happy to answer any questions you may have.
Give us a sense of the duration.
Can you approach the mic, please?
Can you give us a sense of the duration? How long did these tests take?
On the order of hours, a few hours. Wow. They are actually, if you notice that once the model is in place, the execution, the symbolic execution, the generation of tests, the execution of the tests, and comparing the state of the network, actually is very, it's fully automatic. So it only takes a few hours, no manual intervention here.
What about the plan? What about the pre-work, the creating the symbolic execution?
Okay, this is the big part. For us, it took roughly about a week to code the entire thing, but we could just use an open source implementation of OSPF, and we can. We were up and running. If we did that, we were up and running in a day or so. So it depends if you want to start from scratch as we did, or just take an open source implementation. Yes?
Hi. Have you tried this against other companies, other routers?
No, we just tried it on Cisco and Quagga. We also have been told that Lenovo is also vulnerable to some of the vulnerabilities we have found, but we do not have any further information about this. That's it. Okay.
Do you have an airtight way of verifying the validity of the symbolic execution compared to the spec? Or do you just have to heuristically, I found a deviation between the symbolic execution model and this real-world implementation, and then inspect the state of both of them to determine whether it's your bug or their bug?
Okay, I think I understand the question. When we have the network model, it's just a program that can have bugs too. So it may be possible indeed that if we have a deviation, then the bug is on our part, on the model, right?
Or even a false negative if you happen to make the same implementation error that the system under test made.
I think this will be a very slim chance, because if we actually code independently, so the chances that we make the same type of errors are pretty slim, but yes, it is possible. It is possible. At the end, our method finds deviation between two parts, the network model and the router. If there are no deviations, then we cannot find the vulnerabilities.
But since you're intelligently inspecting the deviations,
yes,
you can tell, oops, my bad, versus Cisco's bad.
Yes, of course. The deviations are detected automatically, but still we need to manually inspect them to make sure that there are true deviations or true vulnerabilities.
Thank you.
Okay. Yes, please, on the right.
What type of output are you getting from the routers when you do the real execution? So you're sending the packet towards a GNS3 simulation, And what sort of output are you getting from the routers? Is it the routing table or
Yes.
is it
Yes, in our case, the relevant state for the OSPF is the routing table, which can be easily retrieved from each router just by the CLI commands.
Cool. And also another question: when you have the symbolic tree, you have the end result from all the paths. You have error or end. What you're looking for in the simulation would be a difference between those two. You don't get only the errors or only the ends. You just get, okay, in the simulation, I got an error. I should get an error also in the standard model.
Yes, specifically, I look at the standard model also at the routing tables. So actually compare the routing tables in the standard model to the routing tables in the real network.
Okay, but you should get, if I got an error or a path that leads to an error, I should get an error on the symbolic tree, and that's no deviation.
Yes.
If I got a good end from the simulation and an error on the standard model, that's a deviation.
Yes, if I should get the same output in the network model as well as the actual routers. Yes.
Okay, cool.
Yes, on the left here. Oh.
Hi. So.
Sorry.
Given that we accept there might be bugs in the model implementation itself, I'm wondering if it might be really useful to pit black box routers against each other and see who's standing out from the crowd rather than comparing with only one model implementation.
Actually, you are absolutely right. It can also be done. It's actually a very clever thing to do, actually. Just try find deviations of routers against each other. And probably not all routers will make the same mistakes, the same bugs, and then you will be able to show actually maybe a specific router that deviated from other routers, but still you need to have at least one of the routers should be open source implementation. You can never have only black box routers because you still need to do the symbolic execution to generate the tests, and the symbolic execution is run on an actual software, on actual code. Okay.
Thanks.
How did you make a decision on the authoritative operation of a given protocol or feature based on RFCs purposely being written with verbiage like should and may, to leave it up to the programmer or the builder as to how that feature works?
Well, if we have a should or may in the RFC, so of course, and we implemented in the network model one option instead of the other, so of course we do not consider it a deviation if the other router, if the black box router implemented something else. This is not a deviation. Only if a deviation is considered if the standard protocol stated that it must be done this and that, in this and that way, and the router, black box router, failed to do so.
Thanks.
Yes.
Yeah. Have you thought about building an open source tool to make this type of analysis?
Actually, we were indeed would like to upload all of our code, as well as the network model and all our scripts to the web. It will be in the updated slides when we upload it to the Black Hat site, and you can see a link to the code. And actually, yes, you can use it as an open source, of course.
Okay, thank you.
Okay, so with that, I thank you very much.